Well, thank you very much, Philip, and thanks to all of you who are taking time out to attend this presentation. I'm very thankful to have the opportunity to make this presentation. I was supposed to give it at the Partners Conference a couple months ago, but came down with a nasty bug. So I'm kind of taking a rain check and happy to be able to do this. I guess just by way of introduction, I think tree selection is becoming more challenging as conditions change faster in the future. I view trees as a long-term investment, and so I'm hoping to provide some new information on approaches to tree selection and some of the new models and science that you can use to provide maybe a more nuanced approach to tree selection and make it more efficient and make sure that our trees can provide multiple functions for a long time. So I guess one point just to begin with is that our good health depends on trees, and our team has been quantifying and monetizing the eco-services of trees for a long time. But I'm really excited by the recent work by many other scientists who are kind of putting the connection between trees and our health. And so there's a lot to learn and a lot of exciting research going on. I'm going to talk about some of the challenges we face, and those are going to be in the context of California, where our work is primarily located, but hopefully some of the approaches and some of these issues are transferable and will be of value to you even though you're not living in California, practicing in California. So I'm going to talk about our climate-ready tree study, urban tree database, and some of the science related to estimating carbon stored and rainfall interception by trees. So I'll begin with one of our first challenges, which was the California drought. We came out of a 4-year drought, multi-millennial return interval, really unprecedented. And that drought is now recognized as a condition that we're going to see more of in the future. In fact, it may be more the norm than anything as our region in the Pacific Southwest becomes more arid. And we have kind of two signals at work in our cities, and one is the greenhouse gas signal, which causes warming, but the other is the urban heat island, and that adds a whole layer of complexity because of the spatial variability of the urban heat island. And you can see here in the Los Angeles area where it goes from a degree, less than a degree, close to the ocean to as much as 10 degrees Fahrenheit inland. And so unfortunately, many of the disadvantaged communities are in areas that are warmest, hardest hit. They have the least canopy and the greatest need for tree planting and canopy preservation as one way to mitigate the urban heat island. The forests of the Sierra have borne the brunt of the drought. There's over 100 million trees died over the past 4 or 5 years. But there was an article in the Washington Post that addressed our urban trees, suggesting that many of those are being killed as well. It noted that in 2015, Governor Brown declared a drought emergency and asked people to stop watering their lawns and their landscapes, but he forgot to say that you should keep watering your trees. So this article, as you can see here, said cities are losing millions of trees, and we don't really know exactly how many trees we've lost in urban areas throughout California, but it shouldn't be many because, of course, we were planting the right tree in the right place all along. I say that facetiously because I don't think that was always the case, and what this figure indicates that 8 of the 10 most abundant street tree species in California are relatively vulnerable to drought. And these are the ones with the yellow bars. Many of these are from the southeast, like the sweet gum and the Magnolia grandiflora. And the most ubiquitous is the London plane tree, as you can see. So it's pretty clear that California's urban forest evolved at a time when water supplies were abundant and inexpensive, and really, ample irrigation has underpinned the development of our urban forests. So is that likely to continue? Are we likely to have ample supplies of water for irrigation in the future? Probably not. Another threat, this is kind of the emerald ash borer of California, is what's called the invasive shothole borer. And as you can see, this article indicates it has a stranglehold on the urban trees of Southern California. So it said as many as 1 million trees have been killed by the shothole borer. The problem is that there are over 50 species of trees that are reproductive hosts for this pest. And here you can see the Tijuana River Valley, and 9 months later, over 140,000 trees were decimated by this pest. So it's a real serious concern. You can see on the left the mapping of it in 2014, and then 2 years later it's spread in pretty much every direction in Southern California. So it's kind of working its way north. So this is another challenge that we face. So what we would like is to achieve a gradual transition to a more stable, healthy, and functional urban forest. We want to avoid catastrophic loss of large amount of canopy over a short period of time. And one reason being the economic burdens that places on cities and residents because it's costly to remove and replace trees. The other is the loss of substantial eco-services and human health benefits when we lose a substantial amount of canopy at one time. So from one perspective, you can think of urban forestry as a risk management issue, and when it comes to tree selection, we want to increase the diversity of the urban forest and phase out poorly adapted species. And we can do that primarily through tree selection, and there's reference to an article here where we discuss that. But you may say that it takes generations to phase out species and adopt new species and make a more resilient urban forest. And normally that might be the case, but I was fortunate to work in Tucson, Arizona in the 1980s where there was a drought, and really saw in a period of a decade almost the urban forest go from one that was a city with plenty of lawns and lush trees, blooming like a rose in the desert, to a desert landscape. And it was, the planting of desert trees that spurred change of entire landscapes to much more water-efficient, desert-adapted species. So it can happen in a relatively, surprisingly short period of time. So there's a lot of things we need to think about when we're talking about tree selection, and right now we're thinking of the potential climate change effects as another factor to consider, and recognizing that exposures we have now are not likely to be the case in the future as the climate changes. We have regulatory and market-based incentives that kind of push us in certain directions in terms of the types of trees we plant. In California, the Greenhouse Gas Reduction Fund, which incentivizes planting trees that will store a large amount of carbon, for example, or trees that conserve water. We have sustainability and many cities, are promoting wildlife habitat and plantings for food production, as well as thinking about the end-of-life products. And of course, we always want to minimize the disservices associated with trees, the water costs, root damage to infrastructure, pollutants trees may emit, and litter, as well as the maintenance costs. And then in many areas, infill development is becoming more pervasive, so finding space for trees is a challenge, something we need to consider. And of course, we want to protect the canopy we have and extend the service life of trees that are healthy and provide all the benefits that we are seeking. So it's a long list of things to consider. I'm going to move into our climate-ready tree study, which the goal of which is to gradually transition to a palette of trees that is better adapted to the climate of the future. Working with Natalie Van Dorn, Erica Teach, Allison Berry at UC Davis, and our friends at UC Cooperative Extension. And an article was recently published that gives more information than what I can cover in this brief time. You can see that it's in urban forestry and urban greening. We describe a 5-step process, and I'm going to step through that very quickly. The first is to identify the climate trends that will be influencing trees in the landscape. And we have 3 study areas: the Central Valley, Inland Empire, and Southern California coast. And we used these CalAdapt climate models, which included different scenarios in terms of emissions and climate change modeling for now to the end of the century. And what we found was that warmer temperatures in terms of average minimum temperature, which is and using the USDA hardiness zones, we found in the Central Valley an increase of about 1.5 zones, which is equivalent to 5 to 10 degree Fahrenheit increase in average annual minimum temperature, and a smaller, about a 0.5 zone change in the Southern California areas. There's less certainty regarding future rainfall, but generally more winter rainfall, less summer rainfall. So more arid conditions during the summer. Our second step was to identify promising species. So these are tree species currently not common in our inventories. They may have proven to be successful in other regions that have more arid climates. So for example, in Phoenix, Arizona, they may be doing well. But we don't know how well they'll do here. The planting stock has to be available somewhere so that we can get a hold of some of these trees to plant and trial, and we wanted a diversity of size and genera. So we pulled together horticultural experts, 20 to 30 for each of the regions, and asked them to identify promising tree species. And so, for example, in the coastal Southern California, we had about, I think it was 52 species that were nominated by the experts. 7 of those turned out to be in the inventories in sufficient numbers that we thought they're really not in need of trial because they're being tried in the landscape. So 45 were ones that kind of passed this stage, and so we developed a scoring system for those. And there were 3 risk factors that you can see here: habitat, physiology, and biological interactions. So, for example, habitat, the idea is that the native habitat of the tree and a species that has a wide range of tolerance and grows in, say, a range of soil moistures, soil textures and pHs, and sunlight exposures is likely to be better adapted to the changing climate of the future than one that has a very narrow range of tolerance in its native habitat. We also looked at physiology in terms of drought tolerance, wind tolerance, and salt tolerance. There's a shift towards irrigation using reclaimed water, which can have high levels of salinity. And then we had biological interactions, so of course concerned about potential invasiveness of the tree, the major and minor pests and disease threats, and emerging pest and disease threats. And for urban trees, we added other features that are important. In California, many cities exceed the ozone standards for health, so we were concerned about biogenic emissions, root damage potential to infrastructure such as sidewalks and curbs, the longevity of the tree, carbon storage, which is a proxy for the mature size of the tree, and wood density, aesthetics, tree litter, shade potential, and biodiversity. So each species was scored, and for example, the Southern California coastal region, we came up with these 12 species, and we had 12 for each zone that were selected that met our criteria of having a high score, and we could find them in nurseries to plant for trial. You can see 4 of these are California natives, a couple from Australia, one from the Southwest, a couple from Oklahoma, Texas, Asia, South America, and then one other one. The fourth step then was to plant and evaluate these trees. We have 2 types of sites where the trees were planted for evaluation. The first are what we call reference sites, and these are at UC Cooperative Extension field stations. There's great soil, the trees get good care, well irrigated for establishment, and we planted 4 of each of the 12 species, so we had 48 trees in each reference site. And then we had park sites as a second type of site, 4 parks in each climate zone, and 24 trees, 2 of each species in each park. And of course, the parks had a variety of soil types and irrigation regimes, as well as management practices. And this map shows the park and reference sites for the coastal areas in green, and then in red or pink is the inland climate region. So for coastal, the red star is the South Coast Research Extension Center reference site in Irvine, and then the green dots are the park sites that are pretty close to the Pacific Ocean. And then we have the inland reference site at UC Riverside and the parks in the San Fernando Valley. So we began planting the trees in 2015 in northern Central Valley, and then 2016 we got a lot of help from the Sacramento Tree Foundation, the LA Beautification Team, and volunteers take part in that process. We've been monitoring the sites now for 2 and 3 years. They'll be monitored every year during the 5-year establishment period, and then every 3 years thereafter. And we're measuring height and DBH and canopy diameter. We've taken soil samples at each of the sites, and we're already learning things. For example, this is a ghost gum that's given up the ghost due to Phytophthora, which is a soil-borne fungus, in our UC Davis reference site, and a desert museum Palo Verde that almost grew too well, very luxuriant growth that began to break apart in the winter when the heavy winds came. So there's a lot to learn. You can see this shows just DBH growth over the 3-year period for our 12 species in the Central Valley Park sites, and beginning to see real differences in terms of how quickly these trees are establishing and growing. This is a desert willow, which is a smaller stature tree. I think potentially a really good replacement for the crepe myrtle, which is overplanted in our region, Canby's oak, and the shoestring acacia. So those are 3 trees that appear to be doing pretty well initially. Of course, this is a 20-year study, so it's too early to say if these are going to be good performers in the long run. but early indications are promising. So you can meet the trees and meet the researchers and read the updates and access all of the information at this website. And I would be remiss if I did not recognize all the nurseries like Schmidt and Bowding and the Britain Fund and all the contributors and supporters cooperators who've made this research possible. Which then brings me to the second part of the talk, which is the urban tree database. And I'm really proud of this 14-year effort. Paula Pepper was instrumental in leading this research, where we measured over 14,000 trees in 17 U.S. cities, 171 unique species, and developed growth curves for each of those. One unique aspect was that we aged every tree that we measured, so we were able to establish relationships, DPH from age, and then from DBH height and crown diameter and leaf area and so on. So it's a very unique database for urban trees, unlike anything else, and it's all the raw data and the growth equations are available in the Forest Service archive at the URL given below. And then we have a general technical report that you can obtain free that provides examples of how to use these growth equations and estimate carbon storage, for example. So everything is good except there was one character who couldn't tell the difference between a tree and a utility pole. Anything that was wood and round, he measured it. So I'm a little suspicious about the data there. So just as an example then of how we can use that new information is here in this graph where we have leaf area on the vertical axis and we have year after planting from 0 to 40 years after planting, and we have 4 different types of trees. And you can see this is the magnolia, and I'm kind of equating that with the turtle, which starts slow and stays pretty small. There's supposed to be an animation here, which isn't really working. But then we have the hare, which is the pear, and that starts out really fast, but it kind of levels off because it doesn't have a lot of leaf area. Relatively small stature tree. And then you can see the grizzly, which is the Italian stone pine, which is a much slower to start, kind of hibernates for a while, but then gets very, very large. And then we have the Zelkova, or the lion, which is quicker to start. It's almost as fast as the hare, but gets much bigger, has a lot more leaf area because of its larger, mature size. So it's kind of a way of combining both growth rate, mature size, and thinking about different growth types. So I'm going to tie that together with some of the new science that is helping us better estimate rainfall interception. And many of you are familiar with urban forests as an important strategy in the suite of green infrastructure strategies, really for two reasons. And one is that the runoff can be directed to the soil around a tree, so the soil can store runoff, act as a mini reservoir. And also we have storage in the crown of the tree where the rainfall will be intercepted. Some of that will evaporate in the atmosphere, and that reduces the stormwater or the runoff and overland flow. So the amount of interception that occurs is a function of the total leaf and stem area of the tree, its foliation period, is it in leaf or out of leaf or somewhere in between, and then the surface storage depth, and that is the thickness of the film of rain that adheres to the surface of the leaf or the stem. And why that's important is that we've always been modeling that as a 1 millimeter thick layer of precipitation based on some of the literature from rural forest studies. And we've never really had data on how that varies by urban tree species until now. And this is the paper that was published in a special issue of the Journal of Environmental Quality that discusses this research in more detail. And my colleague Xin-Fu Shao developed this rainfall simulator where we were able to measure the amount of rainfall interception and the depth of this layer for different species of trees through cuttings that we took and placed in the simulator. So what we found was a threefold difference among species in the surface storage potential. At the top of this graph is Picea pungens, or the blue spruce, and which you can see almost 2 millimeters of surface storage depth. Pistachia chinensis, the Chinese pistache, and the coast redwood are well over 1 millimeter. And at the lower end, we have the Pyrus kelleriana, the Callery pear, and the crepe myrtle down about 0.5 millimeter. So quite a difference from the lowest to species that stored the most. And then we also found a fourfold difference for species that were deciduous between when they were in leaf and when they were out of leaf, which was perhaps larger than we initially thought. And of course, the surface traits of each of the different species are a really critical factor in determining the depth of the surface storage capacity. Here you see the Callery pear with a very smooth leaf. Water readily runs off foliage. This is the Canary Island pine. So there is storage at the fascicle where all of those needles come together, and the stems are very rough. So there's pretty high storage. At the same time, the needles are very flexible, so as they get heavy with runoff, the rainfall will run along those needles and drip to the ground or other surfaces below. And this is the holly oak, Quercus ilex, which also has a very rough surface and a very complex form, stores quite a bit of rainfall. So this is so we developed kind of arbitrary surface water storage classes: low, moderate, high, and very high, using the umbrella as an indicator of each species' ability or potential to store. And we have an analog for carbon storage, which is wood density, kilograms per cubic meter, or volume of wood. The idea being that if we have two species of trees and the same volume of wood, the one with the higher wood density will store more carbon than the one with the lower wood density. So we have 4 classes: low, moderate, high, and very high for each of the different species, as indicated by the log rounds. So this is the handout that you can download, and this kind of combines our urban tree database information on tree growth with the information on surface storage, rainfall interception, and carbon storage. And we have the species listed. We have the amount of carbon dioxide stored at 5-year intervals for 40 years in the top graph, and the amount of rainfall interception in the bottom part of this table. We've classified each species into these 4 different, grizzly bear, lion, hare, and tortoise. This is the leaf area at 40 years after planting, kind of the size of the tree at maturity. This is the wood density, and this is the surface storage capacity. So all the data are there on that handout, and this just illustrates the rainfall interception for each of these different kind of growth types, as indicated by the critter and the species. So here we are with our magnolia, which, although it has a fairly high surface storage capacity, doesn't have a whole lot of leaf area, so it's relatively low right from the get-go and stays low. And then you can see the hair, which is the pear. And in this case, as I mentioned, very low surface storage capacity and not a lot of leaf area relative to, say, the grizzly, which is slow to begin with, but has quite a very high surface storage capacity, and the lion or the Zelkova, which starts much quicker than the grizzly and also has a pretty high surface storage capacity and high leaf area and stem surface area. And then the same applied for carbon dioxide storage. And in this case, again, we have the tortoise, which is the magnolia, and it's got moderate wood density, but not a lot of biomass, so it doesn't store a lot of CO2 throughout its lifespan or the 40-year period. We have the pear, which is the hair, which has actually very dense wood, but again, not a whole lot of biomass, but certainly that wood density kind of separates it from the magnolia. And then we have the Zelkova, which is moderate wood density and biomass. And but in this case, compared to rainfall interception, the Italian stone pine actually stores more than the Zelkova in terms of CO2 because it's got higher wood density and high biomass. So just an example of how to put this information together to better predict the performance of trees at different times after planting. So in conclusion, we have the information now to better address different types of benefits and the performance of different species of trees, not only in terms of carbon storage, rainfall interception, but also throughout their lifespan. So we can better predict what trees will be beneficial in what way at what time due to these new models and due to the new biometric science in the urban tree database. And of course, the Climate Ready Tree study, I think, provides an approach for trialing trees that appear to be promising, and then hopefully using those that are best performers to gradually shift the palette of trees to those that will be more resilient in the face of a changing climate. So we all have, I think, been brought up on the Right Tree, Right Place mantra, and now maybe we can add the idea of right purpose and right time. So Right Tree, Right Place is all about matching the tree to the site, the space and the soil. In this case, avoiding large growing trees under low-hanging power lines and looking at the amount of space available at the surface for the tree and the volume of soil that the roots of the tree will in reality be able to use, and matching our choice to those factors. And of course, the social environment of the tree is just as important to its survival as the physical environment. So we need to think about the kind of care that tree is going to be getting. Is that tree going to be considered an ashtray and not good for much other than that? Or is it a tree that is yarn bombed because it's loved and appreciated so much? And of course, we want to think about safety and how long will Natalie be able to stand there and hold that tree up and keep it from falling. And matching trees to the site in terms of infrastructure. And if we don't want to put a tree like this out in front of a retirement center where people are walking around in their walkers and having to deal with sidewalks and curbs that are heaved up. So I'm going to suggest incorporating the idea of context-sensitive selection into the process of tree selection, where we're thinking about not just the site alone, but the context in which that site exists. And that context could be at the scale of the street, the neighborhood of the city. Here you can see a streetscape with a lot of London plane trees. And so that's the context. And, so are we replicating what we have and planting more of those? Or are we trying to incorporate diversity, diversity in species, diversity in age? Here's a planting of plane trees, but in a much narrower condition. So this is so how does that vary from neighborhood to neighborhood? And where are the opportunities to plant trees that are going to be better adapted to the type of space that we're going to be placed in, looking at the long term and their long-term growth. And then at the neighborhood level, is it a young neighborhood where we don't have a lot of options in terms of age diversity because all the trees going in are of the same age, but we have an opportunity to diversify the species. This is the same house maybe 40, 50 years later, and all the ash trees were planted. So in this case, we're faced with rejuvenation of the urban forest because all these trees are maturing at the same time, and we have both age and species diversity as an opportunity to create a more resilient urban forest. And then, of course, there's the city scale, and is the site part of a larger LA of trees in a very important area like you see here, or how does it fit in at that scale of the municipality? And of course, we need to think about maintenance of the tree, stewardship, and the context which that exists. So is that a tree like this tree that has been anthropomorphized? People really love this tree, and they're never going to cut it down because they made it look like a person. So how does that, what's the neighborhood and the whole attitude towards trees in the area where this tree is being planted? So what is the purpose and what is the time frame for the planting? Is the purpose art and complementing the existing architecture and color and form? Is it for shade? Is the purpose storing carbon or intercepting rainfall? And when is it that we're interested in maximizing the benefit that these trees can provide? Here's a planting of redwoods, 5 years old. They're already growing into each other. So its future may be limited in terms of performance. Here's a young ash tree planted too close to the ash that it's meant to replace. It's where it doesn't get very much sunlight. It's competing with the roots of that tree. And here's a dead birch tree. The future is gone because this is a tree very vulnerable to pests and drought that really doesn't have a future in the California landscape of tomorrow. So, the plants we picked today are the trees that the generations that follow us will inherit. They're the trees that our children will be stewarding. So hopefully some of the information in this presentation will help you in making sure that we create a legacy that we can be proud of in the future. So thank you very much for the opportunity to present, and I think we take time to answer a few questions before we pay tribute to some of the leaders of the past.